In this video, I'm going to be working through examples 1, 2, and 3 from your section 12.5 notes. Take a few minutes to glance over the section, observe the formulas that are presented, and when you're ready to work out some details, we can get started with example 1. In example 1, we are looking at finding the derivative of different logarithmic functions. Our first function is natural log of 6x. Observe that the derivative of natural log of x is 1 over x. So this is the natural log of not just x, but a function of x, or a multiple of x. So when you differentiate a natural log function, here's what you want to think about. Take the argument of the natural log, leave it as it is, and put it in the denominator. In the numerator, you'll have the derivative of the argument. The derivative of 6x is 6. So notice the derivative of a natural log function does not involve a natural log. It just turns into a fraction. Now, if we simplify this by reducing those 6's, we find out that the derivative is 1 over x. That's going to be true if we have a natural log function. However, if we have log with any other base, such as on example B, we have log base 10, we're going to get an extra factor in the denominator. So the derivative of y, in this case, we could call y prime. We're going to handle it very similar to what we did the previous one. We're going to take the argument of the logarithm as is and put it in the denominator. And then we're going to multiply by the derivative of that argument in the numerator. So the derivative of x is 1. However, because this is not base e, like our natural log is, this is base 10. So if your base is anything other than e, you're going to have an extra factor in the denominator, which is natural log of that base. Okay, so natural log of the old base is in the denominator of the derivative. Let me write that a little bit neater. So we have 1 over x times natural log of 10. There's nothing to reduce, so really it's a one-liner. It's a simple execution if you know the formula. Let's practice a couple of more. On example 2, we're still finding the first derivative. Notice the base of our log is e. We're dealing with a natural log. So all we have to do is put the argument in the denominator and the derivative of that argument in the numerator. So f prime of x, we start with x squared plus 1 in the denominator. The derivative of x squared plus 1 is 2x. There's nothing to reduce or simplify, so we're done. Natural logs are pretty easy to handle. On example B, this time we have something other than base e. We have base 2. So remember that means an extra factor in the denominator. But we'll start out the same way. For the derivative, we'll put the argument 3x squared minus 4x in the denominator and the derivative of that argument in the numerator. The derivative of 3x squared is 6x. The derivative of minus 4x is minus 4. But again, because it's a base, something other than e, we're going to have this extra factor, natural log of the old base, 2, in the denominator. There's nothing to reduce or simplify, so our derivative is complete. The following formulas summarize all that work we just did. Sometimes the formulas even look more complicated than the actual execution of the problem. So take some time to go over those and commit those to memory so you'll be prepared for the test. When you get ready to work example 3, you can restart the video and I'll work through this one with you as well. On example 3, we're still just finding the first derivative. Notice we have natural log of the absolute value of 5x. Turns out if you have an absolute value around your argument, you can pretty much ignore that when you're finding the derivative. So I'm going to treat it just as natural log of ordinary 5x. So we're going to put the argument of the logarithm in the denominator. The argument is just 5x. And the derivative of that argument in the numerator. The derivative of 5x is 5. We can reduce the fraction. I forgot my prime over there. Better indicate it's a derivative. So y prime then is 1 over x. On examples B and C, Notice we're not only going to have to employ our new formula for differentiating logarithms, but also the product and quotient rules. So on example B, observe we have the product of two functions of x. So in our product rule, we start with the first function as is, and then we multiply by the derivative of the second function. The second function is natural log of x squared. So I'm going to take the argument, x squared, and put it in the denominator, and the derivative of that argument in the numerator. So the natural log of x squared is differentiated. Completing our product rule, we're going to add another term. Notice our pattern. We have same times derivative plus we're ready for the derivative of the first function. The derivative of 3x is 3, and then we'll multiply by the second function as is. If we go back and clean it up, notice I can reduce this one a little bit. I can cancel one of those x's. And we can also take this exponent down in front as a multiplier. Now that's not a derivative, that's just a logarithmic property. So cleaning it up, we have 3x times 2. That gives me, oh, I didn't notice this. We can cancel another x, can't we? Let me go back a little bit. We had 2x over x squared. But in the top, we have x times x, which is x squared. And that cancels the x squared in the bottom. So that first term simplifies nicely just to 6. And then we can call the next part natural log, 6 natural log of x. So the derivative is 6 plus 6 natural log of x. Again, where did that 6 come from? It's this coefficient 3 times the exponent 2 coming down in front because of a log property, not a derivative. So 3 times 2 gives me a 6. Our last example for this video is example C. Notice on this one we're going to have to deal with a log with a base other than e in addition to the quotient rule. So lots of things to think about. Let's begin by applying our quotient rule. When we apply the quotient rule, good rule of thumb is to start by squaring the denominator. And again, that reminds you to lead with that term in the numerator so that you get your numerator going in the right direction. Then I'm going to multiply by the derivative of the numerator. So I'm looking at log base 8 of t to the 3/2 plus 1. I'm differentiating a logarithm. So we know the practice is to put the argument of the logarithm in the denominator and the derivative of that argument in the numerator. So the derivative of t to the 3/2 is 3/2 t to the 1/2. Because notice 3/2 minus 2 over 2 gives me 1/2. But don't forget, because the base was something other than e, in fact it was 8, we have to have this extra adjusting factor in the denominator, natural log of the old base. So we're in the context of the quotient rule. We have the pattern same times derivative minus, now we need the derivative of the denominator. That one's a piece of cake, that's just 1. And then we have the numerator in its original form. All right, so you can relax a little bit because the calculus is done. Next, we need to simplify algebraically. So let's observe in the first term on the left side of my numerator there, I've got t times 3/2 t to the 3/2. Well, if I multiply t times t to the, I'm sorry, that's 1/2. I've got exponent 1 plus exponent 1/2. 1 plus 1/2 gives me 3/2. So I have 3, move down a little bit, 3t to the 3/2. We can move that 2 to the denominator. I'm going to move the natural log of 8 to the left because it's a number. And we have t to the 3/2 plus 1. Whew, a lot of stuff just happened. Did you keep up with all that? So again, we did t to the first times t to the 1/2, and that gave me t to the 3/2. The 3 from the 3/2 landed right here. The 2 in this denominator moved to the main denominator here. And then we had the other two factors, natural log of 8 and t to the 3/2 plus 1. Okay, so we've got that term simplified. And on the second term of my quotient rule, it's pretty good. I don't need to do a lot to that one. Just going to copy it down, and the denominator was good to go. Okay, so we made a little progress, but notice this is what we call a complex fraction. A complex fraction is basically a fraction in a fraction. We only want two levels for our fraction. We want a numerator and a denominator. So what I'm going to do is multiply the top of this fraction and the bottom of this fraction by the denominator that I see in the numerator. So I'm going to multiply both terms by this denominator. Here's what it's going to look like. 2 natural log of 8 times t to the 3/2 plus 1. I'm going to multiply the entire numerator by that. I'm going to put it over 1, just be clear that it belongs to a numerator. Then I'm going to do the same thing to the denominator. So essentially, I'm multiplying this fraction by a real fancy 1. But because I have two terms in the numerator, I'm going to need to distribute this across that numerator. Okay, the good news is when I distribute across that numerator, when I multiply it to that first term, that whole denominator is going to cancel. So we just end up with a cute little 3t to the 3/2. Okay, because the 2 ln of 8, t to the 3/2 plus 1, that canceled. Now, when I multiply it by the second term, that log base 8, we're just going to get a mess of a term here. It's going to look like, I'll put this one first because it has more detail, times log base 8 of t to the 3/2 plus 1. Okay? And then in the denominator, we'll just glue all this stuff together. 2 natural log of 8 t squared. In fact, so the t squared doesn't accidentally join the argument of our log, let's call it 2t squared natural log of 8 t to the 3/2 plus 1. Notice everything in the denominator is multiplied, so you can multiply in any order because multiplication is commutative, and you'll get the same thing. So it looks a tiny bit better than the last step in the simple fact that it's no longer a complex fraction, but it is still a pretty complex answer. I hope these videos are helpful. You have enough information and enough tools, enough formula to go ahead and complete the notes. You are ready for the Chapter 12 test after you've completed your homework and studied a little bit, so let me just say good luck on the test.